You've seen them, right? Robotic arms that can see and pick up specific objects, autonomous drones zipping through the sky, cars that drive themselves. We are truly in a golden age of robotics. These machines are smarter and more capable than ever. But have you ever stopped to wonder what's actually going on inside that metal shell? What's the secret sauce that makes it all tick? Well, it turns out the answer for a huge number of modern robots is this incredibly powerful partnership between a software framework called ROS and the programming language Python. They are the invisible brain and the nervous system behind the scenes. And today, we're going to break down exactly how they work together to make this revolution happen. All right, let's get into it. So, here's the plan. We'll start by looking at what we mean by the robot's secret brain. Then we'll dig into what ROS actually is. After that, we'll see the clever ways robots use it to talk. We'll explore why Python is such a perfect fit for all of this. Then we'll check out the virtual playgrounds where these robots are born. And finally, we'll see how it all comes together to build the amazing robots that are already out there changing our world.
Okay, so let's start with that hidden brain. You know, when you see a robot doing something amazing, it's really easy to just focus on the impressive hardware, the powerful motors, the high-tech sensors, but that's really only half the story.
See, the real quantum leap forward we've seen isn't just about better parts. It's about the incredibly sophisticated software that acts as the robot's central nervous system. This is the code that has to coordinate every single thing, the eyes, the arms, the wheels, the sensors, and get them all working together in perfect harmony. That's where the magic really happens. And right at the very heart of this software revolution is a framework called the Robot Operating System, or just ROS. But honestly, its name is a little bit confusing. Yeah, despite the name, ROS isn't an operating system like Windows or macOS. It's much better to think of it as a universal translator and a super efficient messaging system built specifically for robots. It's basically a standard set of rules and tools that lets all the different parts, whether they're hardware or software, talk to each other without getting their wires crossed. To really get a handle on this, let's use an analogy. Think of a big company. You've got your marketing department, your engineers, your sales team. They all do very different specialized jobs, right? But they absolutely have to communicate to get anything done. Well, ROS is like that company's entire internal communications platform. It's the email, the Slack channels, the public memos, all rolled into one efficient system. So if we stick with that company analogy, let's look at exactly how these different parts of a robot talk to each other using the rules of ROS. It turns out there are a few key ways, and each one is designed for a very different kind of conversation. First, you have the specialists, which are called nodes. Then they have three main ways of communicating. They can send out public memos called topics, they can make a direct request, which is a service, or they can manage a long-term task with an action. Let's break each of those down. First up, nodes. You gotta understand that in ROS, basically everything is a node. A node is just a small, self-contained program with one single, focused job. The camera has its own node. Each wheel motor has a node. The little gripper on the end of the arm has a node. In our company metaphor, these are the individual employees, the accountant, the designer, the engineer. Each one is an expert at their one thing. Okay, so what if one of these specialists needs to share information with, well, anyone who might be interested? It uses a topic. One node, called a publisher, just continuously broadcasts data out on a channel. Think of the camera node constantly streaming video frames. Any other node that needs that information, we call it a subscriber, can just tune in and listen. It's a one-to-many broadcast, exactly like a company-wide memo. But sometimes, a memo isn't what you need. You need a direct, two-way conversation. That's a service. In this case, a client node sends a very specific request to a server node, say, "Hey motor, can you rotate exactly 45 degrees?" The client then just waits until it gets a simple confirmation back. Yep, done. It's a clean request response, and it's perfect for quick, specific commands. And what about the big stuff, the complex, long-running jobs? Well, that's where actions come in. This is like a project manager assigning a major task. A client node sends a goal like, navigate all the way across the room to these coordinates. The server node gets the goal and starts working. But, and this is the important part, it sends back continuous feedback updates along the way. Okay, I'm halfway there, encountered an obstacle. And then finally, when the whole job is done, it sends back a final result. So ROS gives us this incredible, structured way for all the parts of a robot to communicate. But how do developers actually write the instructions? How do they tell the nodes what to do? Well, that's where the second hero of our story comes in,
the programming language Python.
So why Python? I mean, of all the languages out there, why did this one become the go-to for robotics? Well, a few huge reasons. For one, its syntax is super clean and easy to read, which means developers can try out new ideas and build prototypes incredibly fast. But the real superpower is its massive collection of free libraries for really complex stuff. We're talking AI, computer vision, heavy-duty data crunching, you name it. This amazing open source world of Python just plugged perfectly into the open source world of ROS, creating this powerful, flexible, and free platform that closed proprietary systems just couldn't keep up with. And this right here shows you the absolute magic of that partnership. A developer might write just one simple, easy-to-read line of Python code, something like bot.arm.goto_home_pose. But underneath the surface, ROS takes that simple command and conducts an entire symphony. It triggers a cascade of perfectly timed ROS messages and actions, talking to the shoulder node, the elbow node, the wrist node, ensuring every single joint moves in perfect coordination. It's beautiful simplicity on the surface, hiding incredible complexity underneath.
Okay, so we've got our communication framework with ROS and our control language with Python, but building and testing code on a real, physical, and often very expensive robot is risky. What happens if your code has a tiny bug that makes a $50,000 robotic arm smash itself into a table? Yeah, that's where simulation becomes absolutely essential.
Before you can put a robot into a virtual world, you first need a digital blueprint of it. In the ROS world, that's called a URDF file. It's basically a super detailed text file that describes every single physical aspect of the robot. Every link, every joint, how far it can move, how much it weighs, where the sensors are, everything. Once you have that digital blueprint, you can load it into a simulation tool like Gazebo. Gazebo is basically a video game engine for robots. It creates a 3D world with realistic physics, gravity, friction, collisions, the whole deal. This lets developers run their ROS and Python code on a perfect digital twin of their robot. They can test, find bugs, and perfect their logic 1,000 times over, with zero risk of breaking expensive hardware.
So when you put it all together, ROS for the communication, Python for the brains, and simulation for safe testing, you get this incredibly powerful toolkit. Now, let's just step back and look at the kind of amazing things this combination is making possible out in the real world right now.
This setup is the engine behind some of the coolest fields in robotics today. It's what allows cobots, collaborative robots, to work safely right next to people in factories. It's how you get swarms of drones to coordinate on a single mission. It is the fundamental software stock for countless self-driving cars and autonomous drones that have to see and navigate the world. And it even lets us hook in advanced AI so a robot can be trained to recognize and grab a specific object. The key takeaway is, this isn't some far-off future. This is happening today. And maybe the most amazing part is that because ROS and Python are open source, these mind-blowingly powerful tools are available to everyone. Students, researchers, startups, hobbyists all over the world. It has created a global platform for innovation that's just getting bigger and better every year. And that really just leaves us with one massive, exciting question. With tools this powerful and this easy to get your hands on, what incredible things will the next generation of robots be able to do?